Okay, thank you. So I'd like to start by thanking the organizers, both for putting together a lovely conference and for inviting me to speak at it. Now, most of what I'd like to talk about today is joint work. So some of the work that I'm going to be talking about earlier that I'm using as background and motivation is past work of mine with Matt Emerton. And towards the end of the talk, the new stuff is largely work in progress that will be joint with my student, Gil Moss. So I'll try to be clear as we go about where credit is due. So let me start by introducing some notation. Let's take f a finite extension of QP, and we'll take Gn to be the group GLNF, and we'll be interested throughout in the representation theory of GLNF, and in particular in its modular representation theory in characteristic L, where L is different from P. So let's let little k be the residue field FL bar, and capital K will be the field of fractions of the Witt vectors of little k. So the main question that I'm interested in studying is the question of how the local Langlands correspondence varies in algebraic families, say for algebraic families of Galois representations. And well, usually the Langlands correspondence is formulated as a bijection of representations, where on the one hand you have Frobenius semi-simple representations from WF to some algebraically closed field of characteristic 0. And on the other side, you have irreducible, admissible representations of Gn. But a moment's thought about this will convince you that this is really not very well suited to studying variation in families. One of the easiest examples to consider over here is the case where this representation is a direct sum of characters. And then generically, if you have a direct sum of characters, the representation that gets associated over here is some infinite dimensional parabolic induction. But of course, you can specialize these characters so that they differ by a cyclotomic factor. And then the dimension of the corresponding thing over here drops to 1. So that's not so well behaved. But fortunately, there is a modification of the local Langlands correspondence that's due to Breuil and Schneider, and that'll denote by LL prime. I will try. Okay, so now this is no longer a bijection, it's just a map, but it still associates in a canonical way to every Frobenius semi-simple representation of the Weil group, and indecomposable, but not necessarily irreducible, representation of GLN, still admissible. So maybe I'll put that over here. So roughly how this goes is that in the usual construction of the Langlands correspondence, something over here is a direct sum of what are called generalized special representations. And to each of those, local Langlands associates a generalized Steinberg representation over here. And then in general, one takes if you have a direct sum of those, the corresponding thing over here, to get the corresponding thing over here, you take a parabolic induction of those generalized Steinbergs, suitably ordered. And then that parabolic induction will have a unique irreducible quotient, the Langlands quotient over here, which is the target representation. And in the Breuil-Schneider correspondence, rather than taking that quotient, you just take the whole parabolic induction. And so you can see why that might behave better in families, because suddenly you don't have to worry about new smaller irreducible quotients appearing as you specialize. Okay, so with this adaptation, it's possible to at least give a conjectural statement of some kind of local Langlands in families result. And so this is the joint work with Matt Emerton that I was alluding to earlier. So this is actually a result purely due to Emerton for GL2, and then the generalization to GLN is due to both of us. So let's let A be a reduced, complete Noetherian, sorry for the adjective salad here, flat, local WK algebra with residue field K. And let's suppose we have some nice family of Galois representations, GF to GLNA. Then what we give is a sort of uniqueness result for a possible candidate for local Langlands in families over here. So what we show is that up to isomorphism, there exists at most one corresponding family that interpolates the Langlands correspondence. So what should this be? This should be an admissible A adjoin Gn module, which we're going to denote by Pycheck of Rho, with the following properties. So first of all, for technical reasons, we want Pycheck of Rho to be A torsion free. Second of all, this module really does, at least generically, interpolate the local Langlands correspondence across the family. So one way to say this is to demand that for all eta minimal prime of A, you can look at, so notice, by the way, that the conditions on A imply that eta will be a characteristic 0 prime, and also that A embeds into the product of its localizations at all minimal primes. So this thing, you can really hope that this thing might be determined by its localizations at eta. And what we demand is that Pycheck of Rho should almost correspond to Pycheck of Rho eta should almost correspond to Rho eta via Breuil-Schneider, but for technical reasons we have to do something a little bit funny. So we apply the Breuil-Schneider correspondence not to Rho eta, but to Rho eta dual, and then we take the smooth dual of the result. That's to cause the generic part to come as a quotient rather than as a sub. F over QP, yes, but F is just the GLNF. This is, yes. This works over any algebraically closed field of characteristic 0. And in fact, you can descend it, so it works for these fraction fields as well. Okay. Yes. For the everything in the Breuer-Schneider correspondence has a unique generic socle. These things will all have unique generic co-sockles. And in fact, that ties very well into this next condition, which is a condition that sort of rigidifies this whole picture and is where the uniqueness really comes from, which is that if you specialize at the maximal ideal, so you base change down to the residue field, what we demand is that this has a unique, well, let's say has an irreducible generic cosocle and no other generic subquotients. So generic means it has a Whittaker model. In other words, so another way to say that is if you look at the group of unipotent upper triangular matrices, there's a certain class of characters on it called generic. And another way to say this is that the co-invariance via one of these generic characters is non-trivial. Okay. So this is just a uniqueness result. It says nothing about existence. I said that rho had to be nice. No, I said the coefficient ring had to be nice, and this is what it means. Okay, so this is just an existence result, but the obvious conjecture to make here is that these things actually exist. Pycheck of Rho exists for all rho. And this is, the conjecture is also, of course, joint work. Now, a lot of these conditions look like they're fairly technical, and so it's important to take a step back and ask if we've put the right conditions on things here. But fortunately, there are examples where these things arise in nature. So in particular, these show up in the completed cohomology of the tower of modular curves. And this is a result due to Emerton. So if we take sigma, some finite set of primes with p and L and sigma, and we look at integers n divisible only by primes in this set sigma, then you can build a completed cohomology module out of these. So that's the inverse limit over R of the direct limit over these n of h1 of x of n with coefficients, let's say in wk mod L to the R wk. So this is usually done with the roles of P and L reversed, and I apologize for that because I'm going to have to mention the ell-adic Langlands correspondence in a moment, but this will be the only time when that is really an issue. So let's call this h1 hat. And then the point is that Emerton shows that this h1 hat, that if we localize at nice m, so if we have m a non-Eisenstein maximal ideal of a suitable Hecke algebra T, then Emerton shows that h1 hat m has a tensor factorization. So there's some factor at L that comes from the ell-adic local Langlands correspondence that I'm not going to talk about. And And then there's a Galois factor, which is just the Galois representation rho m over the Hecke algebra Tm. And then the remaining factors, I need a name for another prime. Let's call it R. Are just, and here I'm going to have to, unfortunately, put duals in again. Pycheck of rho m dual restricted to dr. Whole thing, this is a smooth dual. So those duals are showing up again, and the reason you can formulate this entire theory without the duals, but then I would have to tell you what a co-admissible module is, as opposed to an admissible module. So the point is that what we should take away from this is that in a global context, these families naturally appear as tensor factors of some nice global completed cohomology module. Okay. So we'd like to be able to build these modules Pycheck of Rho for various rho, and in order to do that, I want to take a somewhat circuitous approach, and in order to describe this approach properly, I'm going to have to introduce the Bernstein Center. So, yes. That's generally correct. I mean, I think I can probably prove that you can do that over something normal. It's trivial to do over DVRs, but this is really a statement about congruences. It's saying anytime you have two Galois representations and you can glue them via a congruence, you can glue the corresponding modular forms, or corresponding admissible representations via a congruence. Yes, that's a good point. And this is actually exactly why I'm about to introduce the Bernstein Center. Because what the integral Bernstein Center will be is an algebraic gadget that encodes all the congruences on the admissible representation side in a nice way. Okay, so. It is not, in general, going to be free. It's easy to write down examples that are not, where it's not free, in fact. So a torsion free is really the best you can do over there, I'm afraid. Okay. So. Yes. It has an irreducible quotient. Yes. Yes, I mean, typically if you look over the various points of this family, when you specialize to a point, you'll get something irreducible. It's only over some closed loci that these subs will actually be subs in that sense. And so they do not, in fact, give you subs of Pycheck of Rho. They're just subs that appear when you specialize by base changing to a field at certain points. I mean, Rho in general, this Pycheck of Rho in general will be indecomposable and generally generated by a single element that is visible in this cocycle. Oh, well, if you have a sub at the generic point, then that sub will be visible over everything, yes, but over that whole component. Cocycle is quotient. Cocycle is the largest semi-simple quotient. So let me So let me introduce the Bernstein Center here. So I'm going to let rep wk of Gn be the category of smooth wk adjoin Gn modules. And I'm going to let Zn denote the center of this category, rep wk of Gn. So very quickly, the center of an abelian category is formally defined as the ring of natural transformations from the identity functor to itself. And what that means from a practical point of view is that it acts on every object in the category compatibly with all the morphisms, and it's essentially universal for rings that act in that way. Let me also introduce a variant of this, which is the classical Bernstein Center Zn k bar, which is just the center of rep k bar of Gn. Bernstein and Deligne give an absolutely beautiful theory of Zn k bar, where they essentially answer every question you could possibly hope to ask about it. So in general, these rings are quite big. They usually have an infinite system of primitive idempotents, I think always in this particular case. But if you think about what it means to have an idempotent in here, that means that you have an idempotent endomorphism of every object in the category that commutes with all maps, and therefore it splits the category into two pieces that essentially never interact with each other. Any map between something in one piece and something in the other piece is zero. So this really breaks up this big category of representations into a bunch of simpler categories. And of course, when you do that, the center gets smaller. And so what Bernstein and Deligne do is they give a description. First of all, they give a description of the primitive idempotents. So the primitive idempotents, let's call such a thing E tilde of Zn k bar. They didn't quite state it this way, but from my point of view, what they did was that they showed that these are in bijection with inertial types. Tau from the inertia group of F to gln k bar. These are just representations of the inertia group of F that extend to the full Weil group. And the point is that if I have some pi in characteristic 0, then E tilde pi equals pi if the corresponding Langlands parameter, I guess that's LL inverse of pi the way I've set things up, has the appropriate inertial type. Rho restricted to IF is equal to tau, and it's 0 otherwise. Okay, so moreover, they show that cutting down by one of these idempotents actually makes the center small enough to be manageable. In particular, great. Oh, that's much better, thank you. Okay, so in particular, they show that EZN is an explicit smooth k-bar algebra. And moreover, they explicitly describe the action on all irreducible representations pi. So you couldn't possibly ask for anything more. Now, of course, it's then very natural, if you're interested in congruences, to ask the same question with k-bar replaced by wk. And here the results aren't going to be as good, because the objects in question become much more complicated. Yes. No. My guess is it's probably just a product, but I'm not going to swear to that. I think that it may follow from the definition that it's just a product, because I'm a little shaky on this, but it seems like to give an endomorphism of the full category, it would be enough to give an endomorphism on each, equivalent to give an endomorphism on each of the blocks. So what am I saying? Well, I'm not quite sure what you're asking, but what will happen. These are smooth representations, yes, but not necessarily admissible. And then that category factors into blocks in this particular way. In particular, for every primitive idempotent, you get a direct factor of the category. I worry a bit about that, because what happens if you take the direct product of something in infinitely many blocks? It's still... Okay. In any event, in practice, I always work with a single block at a time. So I'd rather avoid questions about infinite products, because I find infinite products to be a slightly terrifying object in general. Oh, this is, sorry, yes. Yes, thank you. Okay, so now let me describe the primitive idempotence of E of Zn. So these are going to be finite sums of primitive idempotence of Zn k bar, as it turns out. But formally, you can just parameterize them now, not by representations of the full inertia group into gln k bar, but by representations of the prime to L part of inertia into gln k bar. And again, we require that these extend to WF. And the idea is that if you try to deform a Langlands parameter over fields of characteristic 0, the representation of the inertia group is rigid. But if you're allowed to go down to characteristic L and back, you can, of course, completely change the L part of what's happening at inertia, and the rest of it remains rigid. So we have a bijection like this instead. And again, the question of which characteristic 0 representations fall into a given block is just determined by the restriction of their Langlands parameter to inertia. And from that, it's easy to figure out precisely which simple objects correspond to a given item. Oh, right. I need to mod out by a GK action over here, because now I'm working over WK, and the field of fractions of that is K, which is not the same as K bar. So conjugacy classes here also get merged together. That would happen even if I was considering rep K rather than rep K bar. And then the restriction to inertia happens when you're passing from k to wk. Okay. So what can I say about this? Well, I can't give you an explicit description. I can't give you an explicit description, but I can say that EZN is reduced and L torsion free over WK. And finite type. And moreover, it will not be normal. In particular, if I tensor over WK with K bar, this will give me back the product of E tilde Zn K bar, where let's say tau of E tilde restricted to I, restricted to prime to L inertia, is equal to tau of E. That's not terribly surprising. But what I want to say about this is that the difference between this and this is that it now encodes congruences between different blocks of the Bernstein Center. In particular, if I have two things in here that correspond to Langlands parameters, well, if I have two things in here that become isomorphic modulo L, this algebra will see that isomorphism and will act on them via scalars that become congruent modulo L, whereas this won't see that at all. Okay. So let me now describe a conjecture which relates to this Bernstein Center. So conjecture, let me take rho bar from GF to GLN of little k, some semi-simple mod L representation. Actually, let me not say semi-simple. Let me do this arbitrarily for now. And then let me let R rho bar box be the universal framed deformation ring. So I've been saying all along that what I want is for congruences on Langlands parameters to be reflected in congruences on admissible representations. Now this encodes congruences on Galois representations. This encodes congruences on admissible representations. And so to relate them, what I want to say is that there exists a map F from Zn to R rho bar box that's compatible with local Langlands. So what should that mean? So in particular, if I have X from R rho bar box to K bar, then that gives me X composed with F from Zn to K bar. And what I should ask for here is that the action of Zn on LL inverse, LL of rho x should be given by X composed with F. And because you can show that both these objects are reduced, this property actually characterizes the map F uniquely, if it exists. So I'm going to call this conjecture 2 to distinguish it from that up there, which I should have called conjecture 1. And, well, in my notes, I call this weak conjecture 2, because there's also a strong conjecture 2 that describes the image, but I think for reasons of time, this should be conjecture 1, yes. But I think I'm going to skip that for time reasons. Okay. So perhaps you might anticipate this, given what I've been saying about how both of these conjectures relate to showing that you can glue things via congruences on one side if you have congruences on the other side. But the key point is that now we have theorem, conjecture 2 implies conjecture 1. So I'll prove this in a second, or give a sketch of a proof in the second. But first I want to make some remarks that indicate that now that we know this, we're actually in a much better position than we were before. Because, well, first of all, conjecture 2, as it turns out, is easy after tensoring with k-bar, or even just inverting L. Conjecture 1, by contrast, is not. It's much, much harder because you have to worry about subquotients of parabolic inductions, whereas conjecture 2 only really deals with things up to semi-simplification. This action of Zn really only sees supracuspidal support. So the way you prove this is it's very easy to deform Galois representations over k-bar on the one hand. Let me justify this claim. On the one hand, it's easy to deform Galois representations over a field of characteristic 0. Basically, all you have to do is move Frobenius around. On the other side of the correspondence, we have a completely explicit description of Zn k-bar, and you just write them both down, and they agree. So there's really nothing to this. And then you can descend to L pretty easily. So descend to K from k-bar pretty easily. Everything is Galois equivariant if you normalize it properly. So really what we have is we have Zn adjoin 1 over L and R rho bar box. Sorry, we have Zn and R rho bar box both living in R rho bar box adjoin 1 over L, and and we just have to prove both inclusions. Conjecture 2 is essentially one of those inclusions, and then you can also think about the other inclusion if you like. It parametrizes lifts of rho bar together with a basis lifting a fixed basis of rho bar. Yes, that's right. And this is just because rho bar might not have any nice deformation ring in the usual sense at all. Okay, so if you look at R rho bar box tensor k bar, that essentially parametrizes representations over k bar, and in families, the only thing you can do to deform those things is, this is my. Yeah, no, I'm being a bit sloppy here. I was trying to avoid, there is a global object that this is the completion of that I was trying to avoid mentioning. And secretly in the back of my mind, I'm tensoring that global object with k bar, and then comparing things there. I mean, Zn is a finite type object. And of the Witt vectors, yes. The Witt vectors of little k, yes. And little k was FL bar, but this is capital K here. Yes. So. Okay. Yes. So I mean, so it may be that in my efforts to simplify things, I have actually obfuscated things. But essentially, one can write down a nice object on the Galois side, parameterizing Galois representations, of which this is essentially a completion, and then the GLN invariants inside that object, the elements that are invariant under change of frame, if you tensor with k bar, turn out to be exactly the same as Zn tensor k bar. So that's a statement that only involves finite type algebras. And that's the statement from which you can deduce this by completing at various points. So does that?
I'm just trying to think what you said, like those things to say this again.
Okay. Well. Okay. So anyway, let me. So what else do I want to say? I want to say that in order to prove cases of this conjecture, it suffices. Is the deformation ring torsion free? Yes, it is. It's reduced. It's L torsion free. It's a local complete intersection. Okay. So this action in general will factor through a particular primitive idempotent, and that primitive idempotent is just determined by rho bar, in particular cases, it's often very. In small cases, it tends to be easy to write down generators for Zn, and in those cases, you can see very clearly exactly what the corresponding elements of our rho bar box is. They tend to be traces and determinants of coefficients of characteristic polynomials of Galois elements over there, although that probably isn't true in general. But in any event, as n gets large and as L gets small relative to n, these algebras EZN become increasingly complicated. And in general, the problem of finding explicit generators and relations for EZN becomes very hard. And in those situations, it becomes much harder to try to prove conjecture to. So that's sort of the real obstacle here. But let me say something about how conjecture 2 implies conjecture 1. So let UN sitting inside GN be the unipotent upper triangular, and let psi from UN to WK star be a generic character. And so then just as a matter of notation, there's this top derivative functor of Bernstein-Zelevinsky for V in rep WK of Gn. We define the top derivative Vn to be the psi coinvariance V psi. And let me give a quick definition, which is inspired by the properties we wrote down for pi of rho. So I'm going to call V in rep WK Gn is what's called a co-Whittaker module. Actually, so here A is going to be a WK algebra. And then V in rep A of Gn is co-Whittaker if, first of all, its top derivative is free of rank 1 over A, and second of all, every simple quotient of V is generic. So generic here, generic we can now give a precise definition to. It just means that this top derivative Vn is not equal to 0. So the fundamental example of such objects let me give you two examples of such things. The first example, so this is something that Matt Emerton and I observed. The properties that we demand of Pycheck of Rho imply that Pycheck of Rho is co-Whittaker over the base ring A that appears there. So in particular, its derivative, the second condition basically follows from the genericity condition 3 that we imposed in the list of properties on Pycheck of Rho. And the first condition also actually follows from that, plus Nakayama's lemma and a few other things. So the class of representations we want to construct falls into this general class. The other key example, before I do that, let me also say one other property that you can prove about these things pretty easily is that V co-Whittaker implies that end Gn of V, let me say A adjoint Gn of V, is isomorphic to A. Okay, so I'm going to give one more example of these co-Whittaker models in a second, and it's going to essentially be a universal example. But first I want to notice that for such V, the fact that the endomorphisms are isomorphic to A imply that the action of Zn on V factors through a unique map Fv from Zn to A. So we get a map from the Bernstein Center to A. On the other hand, it turns out that you can construct, in a very natural way, a co-Whittaker module over Zn that then essentially becomes a universal co-Whittaker module. So the way we do this is we consider a space Wn, which is essentially dual to the space of Whittaker functions that people usually consider. And then the theorem, which is originally due to Bushnell and Yar over K bar, and the integral version is mine, is that, first of all, well, okay, let's say this. For all primitive idempotence E, EWN is a co-Whittaker EZN module. So that's part one. And part two is that, in a certain sense, this is universal. Namely, for all V, co-Whittaker in the portion of the category the block of the category corresponding to this idempotent E, we have that EWN tensored over EZN via FV with A. So if this were actually a universal object, we would then say that this lets you recover V directly. It's isomorphic to V. That's not quite true, but what you can say is that it dominates V. It surjects onto V, and this induces an isomorphism. The surjection induces an isomorphism of top derivatives. Okay. So now let me explain very quickly how to construct pi of rho. So let me leave the conjectures up. I'll come back over here. Okay, so, oh, good. Let me leave that up. So given rho from GF to GLNA, we consider EZN to R rho bar box for the suitable choice of your idempotent E. And then the point is that rho comes from some map R rho bar box to A. So now the composition gives you the map EZN to A that you want, and then you can form EWN tensor over EZN A via this composition, and that won't quite be the thing you want, but it will dominate it, because pi of rho, if it exists, is a co-Whittaker module, and the compatibility with Langlands implies that the action of the Bernstein Center has to be given by the map you construct here. So this is almost pi of rho. It is pi of rho, except that it might be a bit too big at the generic points to satisfy condition 2. So as I was saying, this base change EW of EWN to A is almost Pycheck of Rho. It might be slightly off at the generic points, but it will at least have the right supercuspidal support. And then it turns out that there is a small change you can make, an easy fix at the generic points in order to make it precisely the right thing. And that will give you Pycheck of Rho on the nose. So I don't want to get into the details here, but basically it's an easy fix to get Pycheck of Rho on the nose, and so you've proven conjecture 1. Okay. Now, the question at this point becomes, how does one prove conjecture 2? And this is where work of my student, Gil Moss, comes in. So, as I've said already, in the cases where we can prove conjecture 2, the situation is that we have some kind of generating set for EZN, and we can check that the generators actually give elements of R rho bar box. But when n gets large, especially compared to L, EZN gets very intractable, and it's hard to write down a good set of generators and relations. And in fact, it becomes rather difficult to produce elements of EZN at all. So one approach to producing these elements comes from my student's work, which involves generalizing the theory of local constants and gamma factors to this setting. So let me talk about that next. So Gil constructs gamma factors of pairs for families of representations. So in particular, if we have V a co-Whittaker A adjoin Gn module, and W a co-Whittaker B adjoin Gn module, Gn minus 1 module, sorry. And then, well, let's let R be the tensor product, A tensor B. Then we have a theorem due to Moss that says that there exist gamma factors for V and W that interpolate the usual gamma factors of pairs from classical local Langlands. So there exists a gamma factor, gamma of V, W, X, psi. That's a power series, a formal Laurent series, in fact, with coefficients in R. And these have the following properties. First of all, they're compatible with base change separately in A and B. Second of all, if you happen to base change to k bar, these specialize to the classical gamma factors. And then, let me put this over here. And then they have the properties that you would expect from the classical theory of gamma factors. Namely, they're rational in a certain sense that I'll make precise in a minute, and they satisfy a functional equation. So for rationality, we have gamma of V, W, X, psi actually lives in a certain localization, S inverse, R adjoin X, X inverse, where S is the set of Laurent polynomials with leading and trailing coefficients that are units. So this lives naturally inside that power series ring. And they also satisfy a functional equation relating this gamma factor and various zeta integrals coming from V and W. What will be of most interest to us, since these are compatible with base change, is the universal situation where V and W are the universal co-Whittaker modules. So in other words, if we look at gamma of EWN, E prime WN minus 1, X and psi, these are universal gamma factors. Okay, now one place where gamma factors come up in the classical theory is in n by n minus 1 converse theorems, where basically if you have two representations, and the gamma factors of pairs of those two representations with all irreducible representations of Gn minus 1 coincide, then the two representations you started with had the same supercuspidal support. And this suggested to me that since the action of Zn on a module is a proxy for supercuspidal support in general, that that the coefficients of these gamma factors should in some sense generate EZn. But of course that can't be literally true, because these universal gamma factors don't live in EZn, but in EZn tensor E prime Zn minus 1. So there was no way for me to make this precise, and the situation sat here for a long time. But it turns out that there's a very nice way to produce elements of EZN from the coefficients of these gamma factors. Namely, so if I had more time, I'd explain where this comes from, but it turns out that there is a natural map which I'll call theta from E prime Zn minus 1 to the Witt vectors Wk. And now the point is that if you have something in EZN tensor E prime Zn minus 1, you can apply one tensor theta and get an element of EZN. And in fact, if you build sufficiently many elements in this way, you can get a set that provably generates EZN. So, theorem is, I'll be somewhat vague here since we're a bit short on time, but so there exists a collection of elements of EZN of the form, let's say, one tensor theta of ZC for Z in E prime Zn minus 1, and C, a coefficient of this gamma factor. E prime has to vary here over all idempotents in order to get a set large enough to generate, such that for all m, the kernel of EZN to k, the completion EZN sub m is topologically generated by such elements. And this is great because remember that in order to prove conjecture 2, all we had to do was find a set of generators for EZN completed at the appropriate maximal ideal and show that they all lived in the universal Galois deformation ring. And that means that in order to prove conjecture 2, all we have to do is, first of all, construct an analog of theta on the Galois side, which we don't expect to be too hard, and then show that gamma factors of Galois pairs of Galois representations interpolate over deformation rings in the way that one would expect. Now, as I said, this is work in progress. We haven't carried this out yet, but there's reason to be optimistic. And in particular, Seidai Yasuda has shown that when you have a family of Galois representations, Deligne's modified local epsilon constant actually interpolates well in a family over interpolates well over that family. So there's reason to expect that we'll be able to adapt his methods, which are based on earlier work of Lamone, and actually be able to prove conjecture 2 here, at which point every conjectural statement I've made during this talk is justified. So I think I'll stop there.